Welcome to this session on building data lakes in Azure. I'm Dustin Vannoy, and I'll be talking through why we build data lakes, some best practices we follow, and how we build them within Azure. We'll take a look a lot at Azure Databricks and Azure Synapse Analytics, plus some of the other supporting services we use. Do not forget to check out pass.org for all of the other things Pass has to offer beyond Pass Summit, things like SQL Saturdays, virtual events. Go take a look for yourself. And I want to remind you to please fill out the survey. These surveys really help us to do a better job year after year. And if you do it by November 20th, you just might win a prize. So a quick introduction to me. I am a data engineering consultant, and I'm also co-founder of a meetup group called Data Engineering San Diego. I invite you to join us. We are virtual at the time. And the things we talk about, the other types of things I do on the job are modern data systems in the cloud. A lot of times it's building data lakes or modernizing data warehouses with Azure. I use a lot of Apache Spark and Apache Kafka, as well as coding in Python and Scala. You can find more of the different content I create and upcoming events by checking out dustinvannoy.com or follow me on Twitter or LinkedIn, where I tend to post when something new is happening. The agenda for today, we are going to define a data lake, talk a little bit more in depth about what I think a data lake means, and we're going to look at a reference architecture of how we would build that within Azure. That involves Azure Databricks or Azure Synapse Analytics. And we're also going to do a streaming use case as well as the kind of typical batch ingestion. We need data to make decisions. If you think of a company like Netflix that's going to try to decide what content to provide next month and decide what to recommend to users, they need data for any of that to happen. And data is everywhere. It is coming from all sorts of applications. It's coming from a lot of different internal business systems and just publicly available external data, like pulling it in from Twitter. And now, in order to use this data, take advantage of it, we must collect it. And beyond collecting it, we need to analyze it, transform it, store it, model it, things of that nature. And for a lot of that, especially the transformation and cleaning of that raw data, we use data lakes. The simple definition we'll start with is a data lake is distributed storage for big data. So we're probably talking a large volume of data, definitely more than a terabyte. And we are talking about storing it in a way that scales well with modern systems. Now, I want to remind you that to build this, we typically have data engineers do a lot of the heavy lifting. And so you are on the Becoming an Azure Data Engineer track of Pass Summit, and I hope you caught the first session already about what a data engineer is. This session obviously will explore data lakes and some of the building that a data engineer does. And then there's a session about Synapse Analytics that I encourage you to go more in depth on that topic. As well as there's a session about Azure Data Factory, which is more of a no-code or low-code option for doing data engineering than what I'll be showing primarily today. The more in-depth definition of a data lake that I use is that, number one, it's big data capable. It is going to be able to handle a lot of different files that we store first, and we may not necessarily clean and model right away. It is going to have a variety of different data zones. The way I name them right now is the raw data, which is pretty much expected of any data lake. It will have a lot of raw data in it. I also really encourage people to have kind of an intermediate, really workhorse layer that I'm thinking I call enrich typically. This is where we do a lot of transformation and cleaning and store that data back. Maybe we've done a little bit of integration with other data sources, but it's not the final curated certified set that we would show to, executive level people that we would do analytics on and share publicly. That type of stuff, that final certified data, will go in another layer, another zone that, we can call it certified or curated. A lot of times there's a more company specific name that is branded for this part because this is the piece that everyone wants to access and run reports from. Another piece of the definition is that it's ready for analysts. So I've seen data lake projects fail because we build a lot of infrastructure, do a lot of architecture and heavy lifting of data, but we forget to think about how are analysts going to access this data? What permissions need to be set? How much anonymization do we need to do for each data source in order to make it, more readily available to analysts? And what tools do we want to set them up to use? How do we give them some consulting help on getting started if they're new to using data lakes? Those sorts of things. Why do we build data lakes? To go a little deeper, reason number one is because we want to store everything. So I talked about different zones, but we also have a lot of different file formats that come in or data formats that arrive. So you probably are familiar with the limited files like CSV. You're definitely familiar with files like Excel, which can be exported to CSV and leveraged. But some of the formats that a lot of our systems are using and different microservices would be sending to a centralized data lake are JSON or Parquet or Avro or ORC. Raw text data can be coming in, data from APIs, which typically comes in JSON, but sometimes it's a little bit more unique formatting than we would like. These sets of data, these different formats should all be able to go in this data lake without us having to put a lot of effort and energy into collecting that data in the first place. Now, this no schema on write is what enables that. We don't have to model and structure our data right away in order to collect and store it and even allow data scientists to access it. It's great if it has a schema already, but we don't want to have one team of data engineers that has to go determine the schema of everything that we're going to save and use in the future. And then that store everything, we're going to be looking for cheaper storage, and we'll talk about that as we go. Reason number two for data lakes is massive scale. We find that we run out of space if we just keep trying to scale a single SQL Server database bigger and bigger. Beyond the structure and modeling that's required, we have more trouble scaling that than scaling a lot of the tools we use for data lakes. I know Azure SQL offers a lot of good scaling capabilities, hyperscale being one of those. And so it's not all about scalability, but that is a big factor to it. We choose data lakes in order to be able to span hot and cold storage, or that's one of the properties we're looking for, I should say. We want to make sure that really important data that we use more often is really fast to access from the file system we're using. And then we want data that's available. We haven't got rid of it. We haven't archived it where no one can reach it, but we're just going to pay a different price for it. And it's going to be a little slower when they do access it. And we want to pay only for what we need, which is where a lot of the cloud providers come in and make a good offering for being that distributed storage layer. Regardless of what tool is used to access it, having that cloud distributed storage is usually pretty cost effective. Reason number three for data lakes is we want to separate storage and compute. Maybe this is more a property that comes along with it, but as we start to look towards that massive scalability and going to the cloud, we find that we're paying a lot more for the processing than we are for storing the data. And so we want to architect our data analytics systems in a way that we take advantage of that by storing the data in a pretty low cost distributed environment and having different processing tools that we can spin up and spin down. We can scale as needed. And we find more and more these days that different teams would want to use their own tools for transformation and consumption of data. So we probably have some standard way of querying the data from Power BI or something like that. But there's also going to be, kind of data engineers or at least, advanced data scientists within the different business groups that need to do their own processing of data. And they may want to use Apache Spark. They may need to figure out how to access that data from R and do the processing there. A whole lot of options out there that we can support if we go this data lake paradigm. You might be thinking, but what about a data warehouse? What is the difference between a data lake and a data warehouse? This is my attempt to answer that in 1 minute. So I define a data warehouse differently. It is structured. It's not this store everything, get it in whatever format. It is structured and processed and modeled and ready to use. You want users and analysts to have a good experience accessing that data and for that to be easy for them to understand how it relates to, the business language and terminology that they use. We want it to be fast. Another part of having a good experience is that interactive query. I have an idea, I add my filter, I do an extra join, it comes back pretty quickly. I can do this at the speed of thought. And then it's going to support BI tools and concurrent users much better than a data lake typically will. And so you can use Power BI and Tableau and many other tools with data lake systems, but usually you can only have so many concurrent users before you start to have some problems. And you're also going to have trouble getting that live query and response that you may want to do with something like Synapse Analytics dedicated SQL pools, which is a big topic that will be covered in a different session as part of this track. So what I want to do now is take you through some core options that I would typically use for querying the data lake in Azure. So this is the overview slide of Azure Databricks. I'll show you a little bit of this in a moment. And so Azure Databricks is labeled as a unified analytics platform. There's a few other things that can be called that these days, but what that means to me as a data engineer primarily is that it is a managed Apache Spark environment where I get this tool Apache Spark that data engineers love to use, but it comes with security and it comes with notebooks ready to go, and it comes with some machine learning tools that my data scientists will appreciate. And it comes with some optimizations that work really well within the environment you're in. And since it's a first-class citizen of Azure, I have some libraries and connectivity to Azure resources that if I'm standing up my own Apache Spark, I'm going to have to do a little bit more setup and work to get that going in the first place. The other cool thing about this is that you can auto-scale and auto-terminate Apache Databricks clusters. And that is an amazing feature. If you don't know how awesome that is, you probably haven't been doing data engineering for too long, and it's okay. You'll figure it out as you go. But this is a really great feature that that Azure Databricks brings to Apache Spark, and it's going to save us money in the long run and probably help us balance the cost of paying for a really good Spark cluster like Azure Databricks, but having to save all this overhead and save on all of the clusters running nonstop all the time in most cases. So Azure Synapse Analytics actually offers a heck of a lot. Let's talk about the Apache Spark piece first. So Azure Synapse Analytics, much like Unified Analytics Service, I'll call it an integrated analytics service. And so it's bringing a lot of capabilities of analytics and data engineering together into one platform within Azure. And this is built by the Azure teams. It's very well integrated into Azure. The thing that I look at it for building data lakes, though, maybe this is selling it too short, but it's also a managed Apache Spark. It has this notebook capability. You can build Apache Spark jobs similar to how we do it in Azure Databricks. And you can schedule jobs from schedule notebooks and run Spark jobs to do some processing and do some analytics. It also has serverless SQL querying. So if you're used to writing T-SQL on top of SQL Server boxes or really any form of relational database, it gives you a way to write these queries from notebooks, kick them off, and it's all going to happen without you having to worry about the server setup. You're basically paying per amount of data processed by that query rather than having to start clusters, deal with them auto-terminating, plan out cluster size, some of the more advanced things that do come along with working with Apache Spark. There's some other features that are really good, but auto-scale and serverless capabilities ultimately are offered through Azure Synapse Analytics as well. And so I'm defining these things because when you start looking at other options for doing data lakes across all kinds of environments, you'll find the auto-scale and the serverless isn't always as easy as they make it sound. To make sure you know a little bit more about the scope of Synapse capabilities beyond what I'll share more about today. So we talked about Service Apache Spark, which is really for that processing and exploration of data. We talked about serverless SQL, which is for querying the data without a bunch of infrastructure in place. And this could be used as part of the ETL process or for analytics. What we didn't really talk about yet is provision SQL, which is, it used to be called SQL DW. Now it's called, in Synapse, it's now called Provision SQL. And this is your analytics database, really good for data warehousing type workloads where you want that interactive query. You want that really structured data in there. And it's qualified as a massively parallel processing database, which is its own subject and set of systems. That is not really what you use for data lakes. It's more for the data warehousing side of things. And then we have Synapse Pipelines is integrated, which if you know Azure Data Factory, it's the same core, the same foundation, but it's integrated right into your Synapse environment, along with some other integrations that are possible. But this is kind of the quick overview of the data lake pieces, plus the more data pipeline and data warehousing components of Synapse. Now, if you're like me, you like to see this stuff in action. And some of you may not have seen either Azure Databricks or Synapse Analytics yet. So right now I'm going to show you sort of the analyst view. How do we query this from these different tools? So let's dive into that demo right now. We'll start by taking a look at the Databricks workspace, just so we have some familiarity. So on the left, we have a pane that can jump through some different spots, and I'm looking at the home page here. So it kind of gives us some indication. We can create tables through a UI. We can create new clusters. We can set up scheduled jobs. It has ML flow integration, so we can do experiments with ML flow and some other quick links that we can take advantage of. Here it's listing my most recent notebooks, and we'll jump into a notebook in a moment to look deeper. But I want to show you real quick, if I've already created tables, in this case I've only got a couple, those are going to show under this data pane, and I can view some more details by clicking around there. If I want to add a new cluster, I can come to my clusters pane, create cluster, fill out some information. Quite a bit here to know more about. I have a YouTube video you can find to see some of these options, but things I want to point out super quick are that enable auto scaling is a really good option. For a test cluster, you probably want to get rid of that and just go down to 1 worker or 2 workers. Terminate after a certain number of minutes is going to save you money. I go down to 60 minutes or maybe even less for testing. And then we have advanced options. So if you need to set some Spark configurations, which eventually you'll need to do, you can do that here and restart the cluster, or it works fine if you're creating a new cluster as we are right now. And then we can set up our own initialization scripts if we need to install some custom libraries and things like that. We can configure logging, which is a very important step once you start getting to a more production-like cluster. And that's kind of the basic steps to create a cluster in your Databricks workspace. I've already got one running though. It's already got Apache Spark 3.0.1 on it, so we're in good shape. Let's jump into a notebook and start looking at how the query interaction looks. So in this example, we're going to take New York trips data and basically pretend like we're trying to analyze the data and come up with a way to do some real-time routing and maybe let people request rides online. Some of the things that Lyft or Uber would do. We're trying to take our taxi company and do the same thing. And you can get access to this notebook via GitHub at Data Kickstart Databricks Notebooks, and follow along there by starting up hopefully a trial Azure Databricks cluster if you don't have one already. And then going a little into this, the first thing we would need to do, maybe it's already done in a real environment, but we need to create some kind of table, some type of schema on top of data that exists in the data lake. So we're going to create an external table on top of a folder that already has 1 year worth of data, 2019. In this case, it's CSV delimited data. We use a command that looks like this to create the table. You may be familiar, if you've ever used Hive, it's pretty much the same syntax. Sometimes there's little variances in the properties. We can specify a path. In this case, it's actually a mounted drive that I have, but the original location is also included, which is going to be available if you create your own Azure Databricks workspace. So it's Databricks datasets, NYC taxi, and you're going to see like 1.6 billion records. So I copied just 1 year into my own storage for this example. So if we run that, it only took 1 second to create the external table because no data was moving around. I'm just adding a schema on top of files that already exist. Now we actually want to query that data. So if we start with a basic select count 1 from the data set in order to see how many records we have, we end up having 80 million records, 85 million almost. And the thing I want you to see is that it took 20 seconds when I ran this. So with SQL Server, usually there's statistics that already know the row count, and that's going to be a really fast operation for most examples. With a data lake, it actually does need to do some more processing usually in order to know what that row count should be. As we look a little further, we can do examples like select top 10 or whatever we want to do. And so you have pretty basic SQL syntax that you can use, and it's actually going to process a bit slower because it's working with files. It's doing this on the fly. And I haven't actually formatted these files very well. We'll talk more about that throughout this session. So I'm querying gzipped CSV files, which might be what I stored as in my raw layer because that's what I'm given by whatever system I'm pulling this from. But it is probably not how you're going to store that long term. Okay, so that actually took almost 2 minutes to run. So it took quite a while because I had to read in all the data for 2019 and then apply the filter. So there are ways around that, and there are formats that work better, which will be kind of the theme of this demo. But that is a basic query where I select attend records with a filter. You can do things like describe the table and see a little bit more about what kind of columns and data types we're working with. If you want to look at what the files look like under the covers, one way within Databricks is to use this magic operation that starts with a %sign. In this case, it's a file system command. So I just want you to see that here is the way the data is organized. So there's a folder called 2019, and I reference this 2019 folder as basically my table path, and then all of the files within it become the data that gets queried. So let's look at, now we've got this raw table. How do we create something that's going to perform a little better? So this query here is going to create a Delta formatted table. Delta format is going to perform quite a bit better. It's going to use columnar storage and compression and some other optimizations that the Databricks team has built as they built out this Delta format. It is open source, so you'll find it in other Apache Spark implementations, but you might have to add it if you're not in Azure Databricks or Azure Synapse Spark. So next we can query that Delta Lake table. And so when I ran this query, which is just a select top 10 without any filters, it was actually really quick. This is an account. This is a select top 10. It ran really quick, less than a second. And I can see that the data's in there. It looks like it's the right data type. So at first glance, it looks like that query I just did worked out pretty well. And then this is more so to show you that the SQL syntax is probably similar to what you're used to with any relational database. So we can do aggregation like account and an average. We have our from clause to specify the table, where filters, group bys, order bys, and that kind of thing that we can do with SQL on top of our data lake. But all this data is actually stored in files of certain formats and certain schemas applied on top of them. It is not hitting a relational database anywhere. And to take a look at where the data is stored for that yellow trips delta table, you can find that here. And in this case, it's actually partitioned. So we have an extra level where we have folders that have year month equals a particular year and month. And that's going to give us better performance. We also have a Delta log folder, which is going to come along with using this Delta format. We'll talk about that later in the session. So that's your basic view. If you're an analyst or data scientist just trying to query this data, that's your basic view of how you can do it only with SQL. There's plenty of other options, of course, with interacting with Spark, but that is one option that might be familiar to a lot of you. Let's take a look at now the Synapse Workspace. So we're jumping from Azure Databricks over to Synapse. You with me? All right, good. So looking at Synapse, we have recent down here, and so we have some notebooks we can work with. The real quick overview of this workspace is that you have a similar idea of a place where you can go browse data. You can have linked databases and also linked data lake storage. This is actually the same storage location that I was querying from Azure Databricks. We're going to query the same files. And then you have a spot for developing where you create notebooks and store them and name them. This is where you would go to do some Synapse pipelines, which is similar to Azure Data Factory. You have a spot for triggering those pipelines for other monitoring of Apache Spark and jobs and triggers that you've set up. And then we have a place where you can see the different pools that you've set up. So we'll be working with Apache Spark pools, which are part of like the serverless offering within Azure Synapse. And then we'll also look at Azure Synapse serverless SQL pool. So this is the pay-as-you-go on-demand type of option. From the Synapse Workspace home screen, I can go down to my recent notebook, and this is going to show us a few ways of working with serverless SQL. So you'll create a data source if you don't have one already. This is the command, and note that it points to a Azure Data Lake storage container, which is one that I was also using from Azure Databricks. Here's a query that uses open row set format, and I'm referencing Parquet data, which is just another file format that we might use in our data lake. If I run a select top 10 here, we can see that it can actually come back pretty quickly. The results may vary though, since this is serverless, sometimes you'll get a little bit more delay. And then probably more likely is that you'll end up creating some external tables that people will use without needing to call open row set every time. So you would need to drop the table if it exists. You would need to Make sure you have a format for Parquet that you've created yourself. That's just something that you do when you're working with serverless SQL in Synapse. And then from there, we can create this external table that will point to one of these snappy Parquet files. So let's go ahead and run a command to drop the table and make sure the file format's created, and then create this external table again. Okay, that ran super quick. Finally, we run a select top 10, and that ends up taking about 36 seconds, but it may be different the next time we run it. One of the things about using serverless is that the timing varies a little bit more than you would expect in other systems. So still in Synapse, we'll take a look at our Spark notebook. And really, I just took the commands that I used from Azure Databricks notebook and put them in here. The only real changes I did was add the Synapse name as a prefix, and I removed the semicolon because Synapse Spark is very picky about semicolons in these notebooks. So I was able to run the drop table. That ran in about 2 seconds. Create an external table with the same syntax as before. I did have to change the location though to be something that Synapse recognizes. Then I was able to run that select count, a similar timing. It took like 26 seconds to run and got back the exact same count for me. I was able to take that same limit and run that. And then as we look at describe is available, drop table for the Delta format that I did, again, renaming it to Synapse. And then it took a couple minutes, about 3 minutes, I think similar performance, to recreate that table here in Synapse and with the same type of SQL code again. And then finally, that same select statement works. And so all that is to show is that the notebook looks a little different. The Spark cluster spins up a little bit differently. You have a little less control over it in Synapse, but the code's going to be the same. In this case, running a SQL notebook against Synapse was almost the exact same code as what we used in Azure Databricks. So in our demo, we saw querying the data lake via Azure Databricks and Spark SQL commands. We also saw how to use serverless SQL from Synapse. And then I showed that we can use a Spark notebook within Synapse with the same type of SQL code and get the same results. Next, we're going to take a look at reference architectures and go a little deeper into some of the other technologies we use. So we need to start simple by looking at all of the source systems like databases and applications, mobile apps, internal applications used by your business. These systems, you could just use Azure Databricks to import all of that data, probably through batch jobs with this simple picture here. So, once a day, once every 30 minutes, you're hitting a source system and ingesting that data and putting it in the raw zone of your data lake built on Azure Data Lake Storage. So when we do that, we don't just leave the raw data, right? We want to have this enriched, transformed area, and finally a curated area. And so to do that, we would just use Azure Databricks to read the data back in from the raw zone, do some more processing, maybe integrate and join to other data, and then write back to the enriched zone and eventually to the curated zone. Now, as we look at a more realistic setting, chances are that orchestrating these jobs gets a little complicated if you're just, adding jobs into the Azure Databricks workspace, which is a real possibility. And so to orchestrate more complex dependencies, you might bring in Azure Data Factory. So Azure Data Factory, if you've worked with SSIS, you probably, it feels a little familiar when you see demos of it. It can be used as a no-code or low-code ETL tool, much like SSIS, but it can also be used kind of a level up to just orchestrate your Spark jobs or maybe a variety of Azure resources that you have working together to get this data into your data lake. So in this diagram, we might do some simple copy transforms in Azure Data Factory just to go straight from like a SQL Server database into Azure Data Lake Storage, skipping Databricks altogether. But then a lot of what I'll be looking at is using Data Factory to orchestrate Azure Databricks jobs and run one after the other, trigger based on different events that happen. When we talk about streaming though, that's where that bottom part of the image where we have event hubs popping into the picture. Event hubs is this layer that we would stream our data to. The source applications will publish data to event hubs, and then Azure Databricks could be reading real time off of event hubs, doing stream processing, and every so often landing that data in Azure Data Lake Storage, as well as making it available for other applications or live reports, those kind of things. Looking at a simple view again, instead of Azure Databricks, we could substitute Synapse Spark. And Synapse Spark, I think for the batch loads, will offer a lot of the same capabilities. They certainly have different offerings, but you'll be able to do the job with Synapse Spark. Keep in mind though, it's not generally available yet. So I would say if you have some time before you're going live, you could start exploring both, see which one you like better. But if you're ready to go to production tomorrow, it's not quite there yet. You got to wait for it to go GA for most cases. So working with Synapse Spark, another option though we could do within Synapse is kind of a combination of do Spark for some of the processing and do serverless SQL for some of the other processing. And so keep in mind that this could be a combination of serverless SQL and Synapse Spark. But the concepts are the same, right? And so as we go a little bit deeper into the full picture, instead of Azure Data Factory, we'd use Synapse pipelines in much the same ways I talked about for Azure Data Factory. And we'd use Event Hub still as the place that we publish data to from our source applications. But then Stream Analytics is probably the better option than trying to use Synapse Spark for streaming at this point. So Stream Analytics, it's a different programming API. It's going to feel different, but it is an Azure offering that can work pretty well with Synapse. Or you could still use Azure Databricks for your streaming jobs and use Synapse for a lot of the other processing you do. But ultimately, we're landing that data in Azure Data Lake Storage still, just kind of swapping out a few of the components in the architecture. Let's go into Apache Spark a bit more. I've been talking about Spark a lot. Let's define this a little better for you. Let's start with the why. Big data and cloud has just changed our mindset to where we want our tools to scale easily. We want them to be really good at recovering from failures along the way. And we don't want to have to plan right now for how much data volume we'll expect to have in a year. There's a lot of companies where as they get more capability to process data, they start to find way more data that they could have been using this whole time. And everyone thought you couldn't do it. So no one's been telling you to go grab the Twitter data, go grab some external vendor that has all this information that we could use. We can do that now. We don't have to limit how much data we ingest. So it is a fast general purpose data processing API and processing platform. So I like it because I can do my streaming and my batch workloads with it. There's quite a bit of capability there. So if I want to get really good at Apache Spark, there's not many data engineering tasks I can't figure out a way to do with Apache Spark. It has a pretty simple API. Once you get used to it, I think you'll find it's really not that hard to switch between batch and streaming, to switch formats from event hubs to Kafka to a file system. All of that starts to become fairly easy once you get the basics down. But it is parallel compute, and so it's going to run at this big scale, and it's going to have the complexity of any clustered computing. Any distributed processing has complexity to it. And as you get further and further along your journey, you'll end up having to deal with that complexity at some point, but the tool takes care of a lot of that for you. We have the choice of Scala, Python are kind of our main choices for programming in Spark. However, Java and R and C# even are options depending on what system you're using. C# is well supported in Synapse Spark. R is well supported in Azure Databricks, but I would say Scala and Python is where you'll find most examples and most teams actually in production with today. We talked about streaming versus batch. There's also this opportunity to use more core low-level APIs within Spark versus what I'll show you and what I've shown you already is Spark SQL library, where we may not just write full-on SQL statements, though we could, but we'll use this data frame API and do some select statements, some group bys, some similar types of operations that we're used to with SQL. There's also an ML library, so you can do your training, you can just do pre-processing for your ML models. There's a lot of capability you can accomplish with Apache Spark. And then just a heads up, the execution engine, you kind of get abstracted from this with Azure Databricks and Synapse Spark, but you can run on a Spark cluster, which is the way Azure Databricks is working, or you could run on Yarn, which is what Hadoop would run on. And so if you've worked with AWS EMR, or if you've run Spark on top of a Hadoop, it would have been using Yarn as the resource manager instead of the Spark cluster. What's great is you can even run this stuff locally. That's not what we do for production jobs, but for development, we run Spark locally quite a bit. We can get a lot done there. And you might even have some cases where you can just run the job locally for a bit when you first deploy, but over time you expect to have to expand and run on a more distributed platform. So the benefits of horizontal scaling, I want to make sure we get this. Let's go with a simple example. If we were talking about a job that we ask people to do, let's say you're trying to move from one apartment to another. You could hire professionals and maybe you get one single really good experienced professional and they come in and do a great job and you pay them for that work. Or you could just get 10 of your friends, buy them some pizza, and you're going to get the job done probably at least as quick if you have enough people. It's a similar concept, right? We're going to break up this work among a lot of different people, or in this case, in the case of Spark, a lot of different workers, a lot of different servers. Those different servers are going to each take a piece of the task, and then it's going to have to eventually come back together in a coordinated way, and you'll get your results. And so that's the way we approach things with cluster computing. Get a lot of lower cost, less specialized components working together. To look at this more from a system perspective, we have a controller node in Apache Spark that's going to be where we run our driver application. So the driver application is a Spark term for the code that I submit to run. That's going to run from this controller, and then a lot of the operations are going to be spread out among the workers that are in the cluster. Next, I want to show a bit of the Spark syntax. We won't, cover everything you need to know to get started, but between the examples I show and this code we'll talk about, hopefully that gives you a feel for what the Spark API looks like. So we'll compare batch versus streaming. So the first thing to know is a very simple read use case. If we are doing batch, we are going to set a variable, in this case called dataframe, equal to spark.read. We pick a format. I'll use Kafka, which is the API we'll use for streaming today. And then we pass some configurations and call load. You can see on the other side that streaming with read stream changed is pretty similar otherwise. And so the options are probably a little different in this case for Kafka. There's a couple different options with streaming versus batch, but it's pretty similar syntax. And so you can probably imagine if you're writing a big program in Spark, you can kind of switch between batch and streaming fairly easily on the read side. When you get down to writing, after you've done some transformation, it's again very similar between batch and streaming. So in this case, you call either dataframe.write for batch or dataframe.writeStream for streaming. If you have a streaming sync available, in this case, the format of Kafka is a streaming sync that we can use, then things go pretty smoothly. There's a couple of extra options you set, and you'll be able to see those in the example I do shortly. Now, if we're talking about aggregation, there's one more nuance to keep in mind. So you have this data frame object where all your data is read into, and you call a group by on it. So if you're used to SQL, that's very familiar syntax, I'm sure. And you see at the end, I'm doing an average of trip distance. But within that, if I'm doing the streaming API, I also have to add a window, because basically with streaming, you have this like always up to date streaming table. And so you could say you don't want to do an average over all time because this job could be running for weeks on end. You want to tell it just over the last 10 minutes of data that's arrived is what I want to do this aggregation on. In addition to Spark, we're going to be using data lake storage a lot. In this case, it's important to know in Azure that it's Data Lake Storage Gen 2. We abbreviate it ADLS quite a bit for Azure Data Lake Storage. If you are looking around, you might find Azure Data Lake Storage Gen 1, which is a whole different service. Data Lake Storage Gen 2, which is where I'd recommend starting new projects, is built on top of Azure Blob Storage. And so you stand up an Azure Storage account. You can choose to have hierarchical namespace storage, which is what makes it Data Lake Storage. And you get all the features of Azure Blob Storage, but you also get really good Hadoop compatibility, which Spark is using the Hadoop APIs under the covers. It's optimized for cloud analytics. Just the way it's going to store its data is going to be set for these use cases we do. And the cost is pretty similar. It's worth looking into. It's worth doing a POC on, but the cost is pretty similar compared to Azure Blob Storage as well. In addition, it's important to note that the permissions are the POSIX style permissions. And so it's going to work well with data systems. It's going to let you set these permissions at a little bit more granular level than you can do with blob storage. And the data is actually stored in directories. And so you have some copy and move operations that work differently because it's this data lake storage. Event Hubs is an important piece of the streaming side of our data lake architecture. And so it's important to know why we care about Event Hubs in the first place. So what Event Hubs offers us, it is our scalable message broker. And so it's a reliable place that we can stream data to, we can stream events to, and it's decoupled from the consumers, it's decoupled from the destination. So if I am trying to produce data, say I have a web service that is users are watching videos, if we stick with the Netflix example I used earlier, each time they make a click, pause it, maybe a heartbeat that happens as it goes along, that data just gets sent to Event Hubs. Event Hubs going to collect it. It's very resilient and easily scalable. And I don't really have to care about who's consuming that data downstream as the producing application. As the consumer, I get the benefits of data is persisted and stored for a certain amount of time, which is configurable. Typically, we're going to look at several days to a week. And so if my consuming job breaks, I may not need to worry about missing messages for that short bit of time that it's down. I can pick up where I left off and keep processing from there. In addition, it's really nice for analytics if I make a mistake in my aggregation or need to recalculate this week's data with some fixes published to that topic, to that Event Hub. Then I can do all of that without the trouble I would have with a message broker that doesn't persist that data for me. So to see more about that decoupling of producer from consumer, up top we have our producers. They'd be producing trip data in the New York City taxi example, or vendor data, which is probably slower moving. Every once in a while we get a new vendor and update to a vendor, but we'd have a lot of trip messages coming in because taxis are being used all the time. Both of those just produce that data to Azure Event Hubs. That is our broker that we send the data to. And then our different consumers, such as the data lake job, which is probably a Spark job. Maybe it's Stream Analytics. We have real-time reports that we might have written in, D3 or something like that with some kind of service that's collecting the data. And then user dashboards that would be like within the application itself, where a user can see their latest trip information. So all of that's just kind of extracted away from who's producing the data and how it's being produced by Azure Event Hubs. Some key concepts for Azure Event Hubs. The top level resource you'd create for Event Hubs is called a namespace, and it's just a container to hold multiple Event Hubs, and you can hold up to 10 in a single namespace. This is how you do your scaling though. So they share throughput units, which is our unit of scalability within Azure Event Hubs. Keep in mind, this is a PaaS offering, which means we don't have to worry about the servers and all of that. We're just paying a fixed amount for the amount of throughput we want, and we can set it to auto scale within some parameters if we choose to. Now, each event hub within the namespace, that's your equivalent to an Apache Kafka topic. If you're used to databases, think of it a lot like a table. You probably have a similar schema for each message going to a single topic. In our case, we would look at trips would be its own topic and vendor would be its own topic. Probably each of those has a fixed schema for the data that we send to it, and the consumers downstream can choose to consume from both or just one of those. We kind of separate out a lot of the implementation from the consumer, including they can use either the Kafka API like I'll use from Spark, or they could use an Event Hubs API, especially if they're working in C# that might be more comfortable for them. And then, like I said, throughput units are your level of scalability. And just keep in mind that it's pretty easy to turn up the throughput and turn it back down and set it to auto scale, though there is a fixed amount of throughput that you can go to per Event Hub namespace. So you want to look into that a little bit before you set things in stone for the long term. And like most Azure resources, take a close look at pricing for your specific use case. It's a little bit tricky to put it all together, though there are some good tools to try and predict that pricing for your use case. Just a quick note, if you want to use the Kafka API with Event Hubs, you need to have standard tier, not basic. I forget this every time, so that's just your warning if you want to mimic exactly what I'm doing here. So now I'd like to get into the code, show you an example where we load the history via a batch Spark job, and then we do some streaming off of Event Hubs. And we'll take a look at this in Azure Databricks, and we'll talk a bit about the Synapse Analytics view as well. Here I'm in a different Azure Databricks notebook. This one's called Data Lake Load. And what we'll look at is the code that we actually use to do the initial historic load and then the ongoing streaming load. So the first cell here is really just importing some different modules that we need and setting up some variables and setting up a Spark schema. So lines 12 to 29 here show you an example of how you could create a Spark schema in PySpark. There's a few ways to do this, but this is one of the simpler ways to approach this. So we've created a schema for our trip data, and then we can come in and we want to build a lookup table first. This is really just taking the taxi zone data that maps, you can see below, maps the borough and zone to a location ID. And so we have a spark.read command. In this case, instead of using Kafka like I showed in my code examples, we're using CSV as the format, and we're reading in that data, simply renaming one of the columns and then writing that data out to the format of Delta. Once that's written, we can kick off the main part of the job. So again, we start by setting a variable, in this case input data frame, equal to spark.read. We're using CSV format for the history. We do a couple of transformations, and we would do this we have a couple of options how to approach this. From lines 13 to 19, you can see we can take that data frame and apply the with column statement. And in the with column statement, we are saying, give me a new column called year month, or if it already exists, replace year month with the formula that's shown as the next parameter. So in this case, it's a little bit more complicated formula of regex replace, but we also have date conversion and simple division here by taking a column called tip amount and dividing by total amount to try and get our tip percentage. If we wanted to do this more with a SQL format, and this is actually going to perform better because when you use the with column in Spark, it's really nice composable code, but the optimizer that runs under the covers isn't going to interpret that as cleanly. You're going to get a really messy query plan, and it will hurt performance if there's enough with columns and enough transformations happening that way. So with this select expression statement, like we see in line 22, we can take the same concepts, but instead we're basically typing expressions that look like what you might see in a SQL select clause. The function names are a little bit different because these are Spark SQL functions, not T-SQL functions. And once we've done that transformation, so you would either do A or B, you wouldn't have both of these in your real script. We take that output data frame and we join it to our zone data. So we read in our zone data on line 29, we do a join in Spark, and then we're going to specify how we do that join. In this case, a pickup location ID to a zone location ID. Then I'm doing a left join. You can do inner join, left join, right join. And I do a few more column renames at the end to make sure my final data set comes out cleanly. And then I can call a data frame.write. In this case, I will use overwrite mode to replace what's there. I'm a partitioning because we always want to think about partitioning. And I'm saving to Delta format, which I've said is a really nice format for analytics use cases. So that takes 5.76 minutes. That one's a little bit longer, but that was actually processing all of 2019, which is those 85 million records we were talking about. There's some things we could do to tune this and make it run faster. I'm pretty confident about that, but let's focus a bit on the streaming use case now. Here we would need to set up some configurations, set a topic name. In this case, I just call it demo message. There's a little bit of password and security things that you can use. With Azure Databricks, we have this thing called a Databricks secret scope. So I'm using dbutils to make a call to get a secret. Basically what this means is I don't store my password in the notebook, which you do not want to do whether you're in Synapse or Databricks. Here is an example of the config. If you're using Event Hubs for Kafka for the first time, this is probably going to be really useful, but you can come back and reference that later. Once we have our configuration set up, it starts to look a little simpler. We again have a data frame that we set equal to spark.read stream this time, and the format is Kafka. We then do a bit of different transformation. So in this case, I'm reading in JSON records, and so I have to take that JSON record, apply a from JSON transformation here on line 34. Basically what's happening is the initial data comes in as a Kafka record. I'm referencing a column in the Kafka record called value. I cast that as a string, and then I apply the trip schema that we set way up at the top of this notebook. After that, from JSON has gone through, it makes a JSON string, and I just give it the name JSON to make it easy to reference. So what's happened now is I've got this JSON record that I can start to reference JSON.location, JSON pick update. And you'll see down here in this transformations from 41 to 45, I'm doing a similar type of with column. I think I actually copy and paste exactly what I have up above for the batch. And so we're starting to see how once we get the data read in, we converted that JSON into data frame columns. I can use the same types of transformation code that I used with my batch code. The join looks very similar. There are a few differences you need to think about if you're doing streaming joins versus regular data frame joins, but in this case, I didn't really have to set anything special, and I was able to take my streaming data, join into the zone information that's stored in Delta Lake, and finally, I just display the results here. So this is currently able to read some data that is being sent to Event Hubs. Let's watch this thing work live for just a moment here. So we'll refresh that view you had. It's going to show us a little bit of information anytime we call display. A few things that are kind of interesting to see beyond the data frame schema. The query itself, you can see that the input rate and the processing rate, you get kind of some good features if you're using a Databricks notebook. The raw data, if you're used to Spark, you may have seen this quite a bit. You get to see this streaming query output that lets you know what's going on underneath the covers. But probably more importantly for you to see is that we actually have data coming in, which is being written from a separate Python application that I have writing to Event Hubs right now. And so this streaming table that we're displaying here is going to keep growing about 1 record per second, or maybe a couple records per, every second or two. So we're seeing that data just start to build up. And so that's how our streaming job would look in a fairly simple use case, but with some real transformations we would need to do. Another thing to know is that, in this case, I just displayed it to screen, which isn't realistic. When I'm writing the data, one of the possibilities, a lot of times I'm writing back to Event Hubs, but you may need to write to a Delta format instead. And so here's a simple command to write to Delta format. You're going to have to specify a checkpoint location when you're doing streaming writes. And so this is an example of how you would do that. And that would run and continually update this Delta path. And that's where eventually you'll need to think about all the small files it creates and do some special things that Delta gives us to optimize those. A final thing that I'll show you, but we won't spend time on, is often you're reading and writing back to Event Hubs as kind of an intermediate step. And then you'll have another job that's part of the pipeline that reads that that destination topic, does some more processing, and sends the data elsewhere. And so here's just another example of reading from Kafka, reading from Event Hubs with the Kafka API, and writing back to Kafka, to Event Hubs with the Kafka API. So the next thing to look at, and we don't have as much to show, is what this looks like in Synapse Notebook with PySpark. And as you probably guessed from our SQL Spark earlier, it actually looks really similar. The first cell to set everything up is the same. I did change some of the paths, but other than that, it's the same. As I start to get into how do I create that lookup table, remember we created that service zone table, taxi zone table. That's pretty easy and pretty much the same code. Then as I get into that batch data load, again, I'm just able to take Spark code and run it over here in my Synapse Spark notebook, which is great. When we get to streaming, I'm not going to show you streaming because it's not really built into the way Synapse Spark is set up right now. And so I'm not going to recommend streaming from Synapse Spark for very many use cases. You might have some cases where you want to do the extra work to get things set up. But typically that's going to be something where we're going to recommend that you use either Azure Databricks and do what I just showed you, or you go and use Azure Stream Analytics, which is another good option for streaming within Azure. So that was our look at running both a historical load with Spark and an ongoing streaming job, all centered around loading data to the data lake, processing data within our data lake. So we ran that in Azure Databricks, and we also saw that the same code will work from Azure Synapse Apache Spark with just a little bit of modifications for paths and taking into account that you would do streaming a different way. Next, we want to cover some file system best practices as we start to kind of wrap up our discussion on data lakes. So as we said, Azure Data Lake Storage Gen 2 is the go-to storage system in Azure for data lakes. We want to make sure we're partitioning our folders. We want to pick formats that work well for our use cases for analytics. Usually Parquet or Delta formats are going to give us good query performance, and CSV or JSON, like the data comes in as, isn't going to compress as well, so it'll end up taking up more space on disk, and it's not as easy to split if you are going to compress it as if you use Parquet or Delta format. And then small files can be a problem. We'll dig into that just a little bit here. So Spark is really powerful, but in order to make sure it works well, we need to know about some of the shortcomings it's had and some of the solutions we're applying these days. So it's not ACID compliant. Most of the time when you're working with data lakes with Spark, it's easy to get corrupted data, and there's a lot of requirement for the data engineers and others writing these jobs to make sure that you're writing only valid schemas to the right folders, that you're not doing things you don't mean to by running like test jobs against the same folder that your versioned and working well code is using. You want to avoid expecting that it will fail if you give it a bad schema. If you give it data that's in the wrong schema, it's usually not going to validate that when you write, and so you need to take more ownership of that. Small files can be written pretty easily, and they're just not efficient for reading, so we want to look at how we handle that in Spark. And then it has a tendency to read too much data because we don't have indexes like we're used to. So to go deeper on the partitions, which is a really important piece of it, we typically are reading all the data in a directory, which is like all the data in a table when we're using Spark. Even if we're applying filters, it doesn't always get passed down the way you might expect it to. So with partitions, we can make that a lot better, especially with Spark 3.0 and above. It handles that filtering better with partitions. And the way we think about it is that we're going to have one fixed partition scheme. So we saw with the taxi data that some of the time I had it partitioned by year, month, day, so that all of those days would be grouped together, and I could use a where clause that said where day is between October 1st and October 30th, and that would trim down how much data is being read. We are going to use pretty low cardinality columns for partitioning. If we end up with 1,000 partitions a day, then you end up with a lot more small files for most of us. If you have kind of medium-sized data, not the super large data sets. And so you want to make sure that you pick partitions. Day is usually a pretty good one. Customers, sometimes too small, especially if you also want to have the date in the partition path. So just keep that in mind, and just know that like we don't get the same advantages that statistics and indexes gave us in SQL Server. So let's talk about Delta Lake, because this is a specific file format, and we're actually starting to see Delta Engine come about and make a difference in how we query data in Spark, and it takes care of some of these challenges that I called out. So the things Delta Lake's trying to address and does a pretty good job of is it addresses ACID compliance. It helps us with some schema enforcement to avoid that corrupted data. It gives us some options for compacting files, and there's some performance optimizations that, having Spark work with the Delta format, especially if running on Databricks and using their Delta engine, you just start to see some performance benefits that are just a matter of the way the format works with the Spark code these days. So to go into the ACID side of things, what we're really looking for is we don't want inconsistency. We want our data to always be in a valid state. We don't want one user writing to the system to overwrite the transactions we're writing right now. If there is a conflict that can't be resolved by the system, we want it to throw an error to tell me my write didn't go through, and not leave any of that in a partial state. And so that kind of need has been handled by Delta. It's still not going to be your transactional system of record. You won't have your applications writing directly to it to store, banking transactions or sales transactions. But for analytics cases, for this processing where you have a streaming job and a batch job and there could be conflicts, Delta gives us some capabilities around there. And it lets us update and delete, which took a lot more effort without Delta in the past. It gives us some advantages on this small file problem. So with small files, we have too much metadata, and we end up with too many open and close operations that happen because it has to open and close each file. Basically, it's going to end up taking one Spark task per file, and sometimes that's good. But if you have thousands of small files, it's going to end up queuing up a bunch of Spark tasks to deal with it. And if you're doing anything like Hive that uses MapReduce under the covers, I think you're probably going to have more performance issues than with Spark alone. But even with Spark, you'll see some problems. And so without Delta, we fixed this in the past and we can still fix it by scheduling our own written file compaction jobs, basically something like go through yesterday's data and all of the files that my streaming job wrote, which might be thousands, compact those into 5 different files or 10 different files, something like that. And so that gets tricky though, because you still might be trying to write some data to yesterday's partition when that runs, and it becomes a little bit of a headache to work with. So Delta gives us an optimized command that will handle that for us. With schemas, Delta is going to default to validating the schema for you. So it knows the schema you first wrote to that Delta format with, and it's going to fail if there's not a match. However, if it's you're adding a field, if it's a compatible change to that schema, you can set a merge schema to true, and it will try to merge those together and have a new schema that comes out of it after that write happens. The key to all of this is the Delta log. And the Delta log is a folder within your data set. So if my table, my trips table is the directory name, under that I'd have a folder per each partition that I've set up. And I'd also have a folder called Delta log. In the Delta log folder, there's a file per commit, a JSON file per commit. You can go in and try to look around and make sense of it. You'll see some stuff you can read in there. But ultimately, when we're working the Delta format, it's going to use that to know which of the Parquet files that it's writing in those different folders are the latest state of my table. When I run things like the optimize command that compacts my files, it'll also clean up some of those older Parquet tables for me and Parquet files for me, and make things a little bit more efficient. So I'm not storing all of that history forever. And there should be an auto cleanup that's set up. I think you can tweak that property on your own system if the default's too long for you. Some final thoughts for you as we wrap up this session. So you have some decisions to make. If you're building a data lake, Spark is a good choice for building data lakes. Obviously, I believe that. That's why I talked about it so much. If you're running Spark with your data lakes in Azure, I think your main choices these days are Azure Databricks or Azure Serverless Apache Spark, Synapse Serverless Apache Spark. And so in that right now, Synapse Apache Spark is not generally available. We're still watching for when that goes live. We're going to see if they up the version to 3.0 or something closer to it, and see what other sort of changes come with that. And so I think right now you might be using Synapse Spark for some of your analytics and your ad hoc work. But if you're going to production tomorrow, you're probably using Azure Databricks for that Spark work. In addition, there are some optimizations that Azure Databricks has that I'm not sure what those will look like in Synapse Spark. So keep an eye on kind of what those look like in the next several months to the next year. You're probably going to find you want to use both of them if you're going to start using Synapse Analytics, especially with some of the other capabilities that are only in Synapse Analytics. For format, Delta format or Parquet decisions need to be made, as well as maybe Avro has a place for you. Maybe there's some other file formats you need to use. You'll need to think about batch or streaming. I really push people towards try and do streaming for a lot of the ingestion, even if some of the downstream jobs are still batch. That way, when we see more business reasons for streaming, we've got the first part of that pipeline already working in a streaming fashion. And then Scala or Python are typically your go-to Spark languages to use. There's strong community and examples around both. You can be successful on really serious big projects with both of those. C# is starting to play a part over on the Synapse Apache Spark side. And then you have R and you have Java, and you have some options to look at if you're really comfortable with those languages instead. We have some data query decisions. These are going to vary a lot, so I won't say much on them, but we need to know how to assign user access as well for when they are making those queries. And we need to decide how much data goes in the data warehouse still. Do we still need one? Chances are, as of today, yes. The answer is probably yes, but we're getting closer to where that decision is going to be a tough one, and not everyone's going to choose to continue with a data warehouse in the future. Now, do we use Azure Data Factory or Synapse Pipelines as part of our ingestion? I talked about that's a good option for orchestration, and you might want to use some of the copy capabilities. You could go way deeper with those tools if you choose to. You need to know how to monitor the jobs regardless of what tools you use with your data lake. Monitoring, I don't think, is an out-of-the-box, ready-to-go thing yet, so we're still working through hopefully Azure's working through getting more capabilities built in, but there's still going to be a lot of tools working together. And so you're going to need to figure out how to monitor your exact platform correctly. You'll need to think about how we deal with bad quality data, how do we monitor for bad quality data, and think about encryption. So the transparent encryption is handled pretty well. I'm sure your security team will want to make sure they know what Azure is doing, but beyond that, you still might need to do some field level encryption and do some things that are a little more specific to your user data that you need to keep private. And depending on which laws you need to stay compliant with, that changes how much you need to encrypt as well. So I want to wrap up with just, these are some references for you. You can find them in the slides that I've shared. On the bottom is a link to a blog post I did, which you feel free to read it or not read it, but at the bottom are quite a few links to resources I used when I was learning and things that I think might be helpful going forward, as well as the other resources that I put on this page. Well, thank you so much for joining me. You can reach out to me via Twitter, via my website, via LinkedIn. I will do my best to respond to you if you have questions we don't get to in this session. Thanks again for joining.